Okay, so let's look into these examples. Fix two numbers, a and b, with a less than b, and capital A and capital B with capital A less than capital B, and define the set X of functions which are C1 of the interval AB, and such that u of A is equal to capital A and u of B is equal to capital B. Okay, so first of all, we notice that this is not a vector space, because if you sum two functions in here, the boundary conditions will add up, so you'll end up with something which values 2a and 2b at the extreme points. So, however, this is an affine space over the reference vector space V of C1 functions which are 0 at the boundary. Okay, so this means if I have a function u in x and v in capital V, then if I add them, I end up with a function in x. Okay, and we consider functions in integral form, which, as a reminder, they are, so you send the point u in x into the integral from a to b of L of x, u prime of x in dx, where L, capital L, is a Lagrangian defined from ab times r into r. And specifically, in this case, we consider f, g, and h defined as follows. So f is just the square of the integral of the square of the derivative. G is the integral of the absolute value of the derivative, while h is the integral of the square root of the absolute value of the derivative. So these functions are they look at first glance very similar, but they're actually not, because so the Lagrangian depends only on the third argument, so on the derivative. And here we're saying that once the derivative is squared, here the power is p equal to 1, and here the power is 1/2. So the power changes, and we will see that this actually changes drastically the behavior of solutions to this to the corresponding minimization problems. So as I was saying, the goal is to solve the minimization problems for these three functionals defined over the set X, and possibly find the solutions if they exist. Okay, let's start with minimizing the functional f. By remark 2.7, we know that minimizers of f will solve the Euler-Lagrange equation, and the Euler-Lagrange equation is just the equation obtained by setting the first variation to 0. So the idea is to first compute the first variation of the functional f, and to do that we compute the Frechet derivative. So I want to point out that this is not actually needed to compute the Frechet derivative, because as we saw in example 2.2, point 2, in case where a function is Gatto differentiable, then the first variation is exactly equal to the Gatto derivative, so it would be enough to compute the Gatto derivative of f in this case. However, we want to do it, I would like to do this as an exercise, because I don't think we never computed explicitly the Frechet derivative of a function, so let's do it for this very simple case. And the proposition is this one, proposition 2.8. So let's call x tilde the set C1 AB, so continuously differentiable functions on the interval AB. And so this is larger than the space X, because the space X was, we were enforcing boundary conditions. Here we don't need to, we just take the larger space C1 of AB, and this is normed with the C1 norm, which is just the supremum norm of U plus the supremum norm of its derivative. And of course, I mean, f can be defined over the whole set x tilde. We previously defined it only on x, but clearly we can just define it like this. So it's still the integral of the square of the derivative of u, okay, for every u which is a C1 function. So the claim is that f is Frechet differentiable in x tilde with the Frechet derivative given by this operator here. So the Frechet derivative at u is the linear continuous operator defined like this. So if you give a function v to this operator, then you get in return this one. So it's twice the integral from a to b of u dot times v dot, and this for all functions v which are C1. Okay, so how do we compute this? The idea is to employ one of the propositions we saw last time. So if a function is Frechet differentiable, then it is also Gateau differentiable, and the two derivatives coincide. So since the Gateau derivative is defined by a formula, let's compute the Gateau derivative first, and then we show that the Gateau derivative is actually the Frechet derivative. Okay, so we do the converse of the proposition. So to compute the Gateau derivative, we need to compute this limit here. So it's f of u plus tv minus f of u, where in this case u and v are both C1 functions. So this first term can be computed explicitly, and in this case is just the square of u dot plus tv dot squared. And so this is a binomial, so you get the integral of u dot squared plus the integral of v dot squared times t squared, because v is multiplied by t, and then you get the mixed product, which in this case is 2t integral of from a to b of u dot times v dot. Plugging this calculation into the definition here, we get these two terms cancel out. First of all, this one is exactly f of u, so this term here goes away, and you're left with this term here. And so dividing by t this one, you get twice the integral from a to b of u dot times v dot, which is exactly this one. And so the limit, as this does not depend on t, you can disregard this term here in the limit. While for the second one, you get t integral from a to b of v dot squared. Now this is a fixed number, and t here is going to 0, so this term here is 0. And so you end up with this guy here. And so this would be the Gateau derivative of f at the point u in direction v. So we notice that this is linear in v, and as it is always, the Gateau derivative is always linear. But also in this case, it is also bounded, and this is something we need to check. It's not something we require, it's automatic from the definition. And to check that this guy is bounded, we just plug in the definition. So we just check the definition. So the absolute value of the Gateau derivative in direction v, exactly, so it would be just the absolute value of this guy, which is less or equal than the integral of the absolute values. And here we can just take outside of the integral the supremum of v dot, supremum in x of the absolute value of v dot, which is less or equal than the C1 norm, because the C1 norm was defined as the sum of the absolute value of v, plus the absolute value of the derivative, not the absolute value, but the supremum of the derivative. So we end up with this constant here times the absolute value of u dot. And so the supremum of this guy over all the C1 functions, which with norm less or equal than 1, is less or equal than this one, which is finite because u is C1, so this guy here is always finite, the integral. And this shows that the operator norm is bounded, and so f prime g of u belongs to the linear operators, so the dual of x tilde in this case, because we're mapping into R. And this is true for all points u in x tilde. Okay, now we can consider the map f prime g, so the Gateau derivative map, which sends u into its Gateau derivative. And we notice that f prime g is continuous in f prime g is continuous in x tilde. Indeed, if you take u and v in x tilde and you look at the difference with respect to the operator norm, Then by definition this is the supremum of over all w with norm less than 1 of the difference of the function evaluated w. And if you do a calculation, basically you can factor out w and you can bound the so here you will get the integral exactly, so the integral like this from a to b. Let's write with a pen the integral of not a, sorry, but this would be basically u minus v dot times w, absolute value, and then you can just take the absolute value inside like we did here, and the 2 is just a number, it goes outside of the supremum. And now here you can, since you can take outside the C1 norm of w, because here you have w dot, and recalling that the infinity norm is less or equal than 1 in this supremum, so this is always less or equal than 1, and you're left with this guy here, which is just the again, you can take this outside as the supremum, so you get u minus v norm C1 times the integral of 1, so in the integral of 1 would be b minus a in this case. And so you have shown that the function f prime g is continuous, because if you vary v around, we actually show that it's Lipschitz with constant at least 2 times b minus a at worst, sorry. And in particular, so this is f prime is continuous from this normed with the C1 norm and this one normed with the operator norm. Okay, then we can apply theorem 1.9. So basically theorem 1.9 told you that if you have a functional whose Gateau derivative is linear and continuous, and such that the derivative is also continuous as a function from the space into the linear continuous operator, then the functional is Gateau differentiable, is Frechet differentiable, and in particular the Gateau derivative, the Frechet derivative coincides with the Gateau derivative. So here we conclude that f is Frechet differentiable in x tilde, with f prime of u equals to f prime g of u. Okay, let's delete this one. Okay, now that we know the Gateau... Oh no, sorry. Okay, what's happening? Okay, now that we know the Gateau derivative, since x is an affine space, by remark 2.5, we know that the first variation, if it exists, is computed as the limit st that goes to 0 of f evaluated at u0 plus tv minus f u0 over t, where v is a point in the reference vector space. So in this case it's the C1 functions which value 0 at the boundary of the interval AB. Okay. Also, I mean, of course, note that both x and v are contained in x tilde, because, I mean, here in x and v we're just fixing boundary conditions, but in the end they're still C1 functions, so they obviously belong to the set of C1 functions. And also we know that the Frechet derivative is equal to the Gateau derivative, which by definition is given by this limit here. So as we have the same limit written on both these things, we know that the first variation can be computed as the Gateau derivative. And so in particular we have that the first variation at u0 in direction v is just given by the Gateau derivative here. Okay, and again notice that this is all well posed, because the variation here is done on purpose with u0 in x, so this is a function which values capital A and capital B at the boundary, and instead tv values 0 at the boundary of the interval by construction. So f is well defined. Okay, to look for potential minimizers, candidate minimizers, we need to find solutions to the Euler-Lagrange equation, which just means setting to 0 this guy here. The 2 doesn't matter, of course. Okay, so basically now we're just trying to find a candidate minimizer. So we're not proving that it is actually the minimizer, so we can do all the assumptions that we want, and then later we verify that whatever we find is actually a minimizer. Okay, so let's start by assuming that U0 is a minimizer, and then we know by remark 2.7 that the first variation is 0 for all variations v. Okay, if we also assume that U0 is C2, so twice continuously differentiable, we can integrate this term here by parts, and I think I'll write it just one time. The integral by parts is done with respect to this differentiation here. So u dot v prime, and you get u double prime v plus u prime v prime. So using this one, you end up with twice u0 dot v evaluated at the extreme points of the interval AB minus twice the second derivative of u0 times v. And now we know that since in v we have the boundary condition v of AV equals to v of b equals to 0, this term here actually vanishes, because explicitly this would be u dot 0 evaluated at b times v evaluated at b minus u0, sorry, okay, and this is equal to 0 because both of these terms are 0, right? And so we're left with just this term here, and so this is equal to 0 by construction, and so we're left with this equation here, star. Okay, now we just look at this equation and we start to think, okay, if u double dot is a constant, sorry, if u double dot is 0, then clearly this integral is 0. This is saying that this should be 0 for all the functions v in which are 0 at the boundary. So it seems credible that the only possibility is that actually u0 double dot is constantly 0 for this to be true for all the functions v. And so okay, let's just say that u double dot is 0, and we will actually prove this fact in probably in the next lesson, because I mean this fact can be proven if you have the integral of some function u tested against v, and this is 0 for a lot of functions v, then you can actually prove that u must be 0. Okay, and this is called the fundamental lemma of the calculus of variations, which we will prove rigorously next time. So let's assume it for now, since I mean this is not a proof, so we can do whatever. So u double dot is 0. Then recalling that at the extreme points u has to value capital A and capital B, we conclude that u is a straight line. Sorry, let's scroll a bit. We conclude that u must be a straight line connecting the 2 points, the points with coordinate A and capital A, B and capital B. And again, notice that to show that u0 was a straight line, we started with u0 being a minimizer, then u0 solves the Euler-Lagrange equation. Since u0, if you assume that u0 is C2, then we can integrate the Euler-Lagrange equation by parts and end up with this guy, and so this guy has to be equal to 0, and this means forces u0 double dot to be 0, which forces u0 to be a straight line between these 2 points. So I mean, we made a lot of assumptions, but again, we don't care. So we basically just proved that if u0 in C2 is a minimizer for f, then u0 is a straight line. Now our goal is to show that the straight line is actually a minimizer of f, and this has to be done by hand. Okay, so the actual claim is that u0 is a straight line, so assume that u0 is a straight line, then u0 is a unique solution to the minimum problem for f. Okay, the proof. Again, this is very simple because the functional is very simple. Okay, so what we actually need to prove is that 1, f of u0 is less or equal than f of w for all w in x, and this shows that u0 is a minimizer. So sorry, this would be for, we actually need to show this for all points in x, so let's write it for all w in x. So this first point here would show that u0 is a minimizer, and then we need to show that it's actually the unique minimizer, so that the energy of u0 is equal to the energy of some other point, if and only if this point is equal to u0. So u0 is the only point with energy yielding the minimum value. Okay, so we start with 1, and so fix u0, which is our straight line, and some arbitrary point v w in x, and then set v to be the difference between w and u0. And since x is an affine space over v, we see that this guy belongs to v. I mean, even forgetting about affine spaces, the function v, you know that it values capital A and capital B to the extreme points, and also u0 does. So if you take the difference, you see that v values 0 in A and B. Okay, now we just compute the energy of W, but the energy of W, W by definition can be written as, okay, we first add and subtract U0, and then we, okay, so, one second, let me see, this is actually redundant. Okay, by definition W is is given by u0 plus v. And now we just use the definition of f. So f of u0 plus v, this is exactly the integral from a to b of u0 dot plus v dot squared in dx. And so by expanding the square, we get this guy here, so this whole thing here, and then we notice that this first term is just f of u0, and this last term is just f of v. So we end up with this extra term here. So the energy, basically f is not linear, of course, so you end up with this extra term. And now, since u0 is actually C2, because it's a straight line, so now this is not an assumption, it is true. And also, as v is 0 at the boundary, we can just compute this integral, integrating by parts, as before, basically, and you end up with these two terms. Now, the first term here is u0 dot times v evaluated at the extreme points a and b, and this is 0, so this is 0 because v is 0 at the boundary, and also this term here is 0, the second one, because actually u0 is a straight line, so if you take the second derivative you get 0. Okay, So actually this middle term here vanishes completely, and you just end up with f of w equals to f of u0 plus f of v. And since the energy is non-negative, this is obviously greater or equal than f of u0. You just throw away this one in the estimate. Okay, and this shows 1, because w was arbitrary and we showed that its energy is better or equal than the one of u0. And instead, to prove point 2, we already proved that f of w is equal to f of u0 plus f of v. So we have that f of w is equal to f of u0 if and only if this term is 0. And if you look at the definition, this is just the integral of v dot squared. So this is 0 if and only if v dot is constantly equal to 0, which means that v has to be constant. Since v was a test function, so v of a v is 0 at the boundary, plus b constant, this means that v is constantly 0. So recalling that v is equal to w minus u0, we infer that w is identical to u0 as claimed, so there is a unique minimizer, and that the minimizer is given by the straight line. Okay, so the situation for f was existence of a unique minimizer, and we were able to compute that explicitly. Now let's look into the functional g. So the functional g, which was given by, let's remind you the functional, so is the integral of u dot x norm, so absolute value. Okay, we have that the minimum of g of u over the continuous functions with values a and b at the boundary is given by b minus a, which is the difference of the extreme points. So let's also recall that x is the set of C1 functions such that u of a, okay, I don't know why this is not working very well, and u of b is equal to b. Okay, so this minimum is just the difference between these two extreme points, and in particular the minimum exists. Moreover, the only solutions to the minimization problem star are given by the monotonic functions, so functions in x such that u dot is greater or equal than 0. So they are monotonically increasing in this case, because remember that by assumption a is less or equal than b. So in order to connect these 2 points, you with a monotonic function it must be increasing. So let's prove this fact. Let u in x be arbitrary. So let's go below. So u is arbitrary, then the energy, this energy here is greater or equal than the absolute value of the integral, because of the this standard inequality for integrals. Just usually one uses it the other way around, so the absolute value of the integral is less or equal than the integral of the absolute value. And so by this inequality, now we have just the integral of u dot, which is just u computed at the 2 extreme points b and a, and by definition this is b, capital B minus capital A. So we proved this lower bound for the energy. G of u is always greater or equal than b minus a, and this for all functions. Now we notice that this lower bound is achieved, so because we want to prove that b minus a is actually the minimum value, right? So we proved the lower bound. So for example, we could have, obviously we also have this lower bound. G is greater or equal than 0 by definition, but 0 is not the minimizer because we have boundary conditions. So you cannot find a point u in x such that g of u is equal to 0. But if you, hypothetically if you could, then 0 would be the minimizer. Okay, so this means that we proved a lower bound, and now we need to show that the lower bound is sharp. So this is actually achieved by some function in x. And for this function we take the straight line, so straight line between the points a capital A and b capital B, and then g of u0 So this is just the derivative, the absolute value of the derivative. And so the derivative of a line connecting these 2 points is just the difference of capital B minus capital A over the difference between B and A. So it's just this value here, which is positive by construction, by assumption actually. And so, I mean, the integral here is the B minus A cancels with the integral, because you get this is a constant, it goes out, and you're left with the integral of 1 between A and B, so you get B minus A, which simplifies with this, and you're left with this guy here. So we showed that LB is actually sharp, and moreover that is attained by U0. So this tells you that U0 is a minimizer of G over the set X. Okay, and now this takes care of the first part of the statement. We now only need to prove that all the minimizers are given by the monotonic functions. So let's assume that W0 solves star, the minimization problem. Then we know that the energy must be B minus A, because we proved that the minimum is equal to B minus A. And we can do the same calculation as above, and we see that G of W0 is greater or equal than B minus A, this without any structural assumption on W0. And so, since this is the left-hand side here is greater or equal than B minus A, but we also know that this is equal to B minus A. So the inequality here is actually an inequality. So it means that this guy is equal to this guy here. But this is true if and only if the function inside doesn't change sign. So it means that sign of W0 dot is constant, and since A is greater, and since A is less or equal than B, this actually means that this sign has to be positive, because W has to connect 2 points which are at different heights, so something like this, right? Okay, and so this shows that that all the solutions to the minimization problem for G are monotonic. So in this case, as a recap, we saw, So as a recap, we saw that G has infinitely many minimizers, which are all the monotonic functions. Okay, let's go on to analyze the last case, so the one for H. Again, here H of U is the integral between A and B of the square root of U dot. Okay, sorry. Write this a bit better. Of U dot in the X. Okay, in this case we can actually prove that the minimum problem has no solutions, and that the infimum is 0. Okay, so in this case we have no solutions for the minimization problem. Let's see how to prove this fact. So we want first to show that the infimum of H over X is given by 0. So let's define this function here, as in the picture. So basically from A to B minus 1 over n, the function is always 0, is always, A constantly, and then it transitions to the value B in this very small space, which is large 1 over n. So from B minus 1 over n to B, this is just a straight line connecting this point to this point here. Okay, so we are achieving, basically what is happening is that we need to satisfy the boundary conditions to be in X. And so we're saying, let's start with the first boundary condition and let's be constant for most of the time. And then sharply we reach the second boundary condition in a very short space. Because the idea is that n will go to plus infinity, so this interval here will be very small. Okay, so in particular un achieves the boundary conditions. If we compute the energy of this guy, so h of un is just the square root of the derivative. but the derivative is, so this function is constant between a and b minus 1 over n, so u dot is 0 in this part, and so we're left with the integral between b minus 1 over n and b of the function. And now we can just compute the derivative. Here we are transitioning from a to b, capital A to capital B, in a space which is large 1 over n. So in the end, u dot in this segment here actually is n times b minus a. Okay, so here you end up with the square root of n times b minus a, which is constant. You can take it outside of the integral, and so by simplifying you end up with 1 over square root of n square root of b minus a, and this goes to 0 as n goes to plus infinity. So okay, this seems to be showing that the infimum is 0 because we produced a sequence respecting satisfying the boundary conditions, and such that the energy of the sequence is converging to 0, so to the which would be the infimum, right? Because also you have that your energy is always greater or equal than 0. However, there is a problem, and the problem is that this sequence that we constructed does not belong to the space because of irregularity issues. You see that in this point the function un is not differentiable, and we needed un to be C1. So okay, morally speaking, this is the function that you have to think about when you think about why does the minimizer why the minimizer does not exist, because you can construct a competitor which looks like this. And now the only point would be actually to make this, to change slightly this function and make it into a C1 function in a way that the energy doesn't change too much, so that the sequence still goes to 0 in energy. So how do you do that? How do you do that in this case? For example, okay, this is the comment that I just made. So now the idea is to smooth around. Let's show the picture first. So basically this was the corner function un, and we want to construct u tilde n such that this corner here is smoothed out, so you end up with something which is C1 and still looks very much like the original function. Okay, so the idea is that you can just, in this case, for example, you can define the function in the following way. So it's the original function away from the point b minus 1 over n, and then you can connect here, you can connect a polynomial in this red area, and you just ask that the polynomial is, for example, you can just take a degree 2 polynomial, I think in this case, and you just impose continuity for at the points here, so the polynomial has to attach to the function un, and also you have to impose the continuity of the first derivative, so meaning that Pn, which is our sequence of polynomials, at b minus 2 over n has to be equal to un, and same goes for the derivative, so also the derivative at this point has to be equal to the derivative of un, and same to the right corner here, so b minus 1 Pn evaluated at b minus 1 over 2n has to be equal to un evaluated at the same point, and same goes for the derivative. And you can see that you end up with a C1 function. Okay, so, and you're also still preserving the boundary conditions. So un tilde is actually admissible, is an element of X. Once you do this, the only thing that you're left to do is to compute the energy of this guy and hope that is the same as the energy of the un that we constructed before, so of the same energy as this function, is this green function here. Okay, I will not actually do the explicit calculation, but it's not hard to believe that since we are changing the function un in such a small interval here, then the energy of un tilde is equal to the energy of un plus something that goes to 0 as n goes to plus infinity. And okay, so basically this shows that we can actually produce a sequence in X such that it goes to such that the energy goes to 0. Okay, and since the energy is non-negative, so we already know that the energy is not negative, meaning that h is greater or equal than 0. So in particular, we know that also the inf of h, okay, this is really not working. This means that also the inf of h has to be greater or equal than 0, right? So by producing a sequence such that h un converges to 0, we just shown that the infimum is actually equal to 0. Okay. And actually the construction, I mean, here we did a C2 construction with a polynomial, but actually here you can do a C infinity construction, so un tilde can be also C infinity and having similar properties. And I think I will leave this as an exercise in the exercises course, because I mean, being able to round the corner of a function without changing it too much is a trick that we will need also in the future. So it's good if you see it at least once in a specific example. Okay, I mean, so this shows that the infimum is 0, and the fact that the minimum cannot be 0 is, at this point, is obvious, because I mean, you just if the minimum was 0, then it means that there exists some u0 in X such that the energy is equal to 0. And by definition of the energy, this is possible if and only if u0 is constant. So this is by definition of H, if you look at the definition. And so u0 has to be constant, but also you need to have that u0 at A is equal to capital A and at B is equal to capital B. And we're assuming A different than B, so this would be a contradiction. So a minimum cannot exist. Alright, so I think we can conclude the lecture because it's almost time to conclude. And we conclude with a short summary. So we looked into these three functions here, f, g, and h, and we tried to minimize them. We actually did minimize them over the set x of functions c1, which value a, which value some a and b at the extreme points of the interval. And we saw that in this first case here, for f, we had a unique minimizer, which was a straight line between these 2 points. For g, we had infinitely many minimizers, which were all the monotonic functions, so monotonically increasing. And instead, for h, we had no minimizers. So what's going on? So if we look at the Lagrangians, so in these 3 cases, the Lagrangians are given by with this notation here. So L of f would be the Lagrangian of this first guy here. So the Lagrangian here, if we express the 3 coordinates as this is the space derivative, so sorry, the point in space, this would be where you place u, and this is where you place u dot. So the first one is given by p squared, the second one is the absolute value of p, and the last one is the square root of the absolute value of p. So what we observe in this case is that LF is strictly convex in P. And we will see in the future, if you don't know what it means, we will remind the definition of strictly convex. But basically this looks like this, around 0, right? So where this is 0. And so it means that every tangent line basically is below the graph of the graph of the function p squared, right, at that point. So every tangent is below the graph. So in case the Lagrangian is strictly convex, we see that there exists a unique minimizer, and this minimizer is also smooth, because we actually proved that in this case it's a line, right? So it's particularly it is C infinity. Instead, the Lagrangians for G is convex, because the absolute value of P looks like this, but it's not strictly convex. And in this case, we saw that for sure we have existence of minimizers, but we might not have uniqueness, and even maybe they're not even regular, because here they were just the monotonically increasing functions. So you can also have something which is not infinity, right? It is just sufficient for it to be increasing or non-decreasing, to be more precise. And finally, the Lagrangians for h, which is the square root. So this is not convex in P, it's actually concave. And we saw that in this case we have no existence and no regularity. And in the future we will see that these three situations are actually, I mean, basically all that can happen, and at least in this course. And yeah, in this case, in these three cases, you will have behaviors which resemble the behaviors that we saw in these three examples. So existence and uniqueness with smoothness, existence but not necessarily uniqueness and smoothness, and finally non-existence at all. But you're always able to find somehow a sequence which converges to the infimum. And obviously, since you have non-existence, you have also no regularity. Okay, I think this is a good place to conclude. Next time we will look into this what is called fundamental lemmas, specifically, for example, the fundamental lemma of calculus of variations which we applied previously in the example for f, where we showed that we had a condition like this. This was equal to 0 for every function which was C infinity and compactly supported in AB. We will see exactly what this means if you don't know it. And then we saw that if this is true, then this forces U equals to 0. And we will see that this is actually something that you can prove rigorously, and it's actually a very fundamental tool in the whole throughout the whole course. Okay, then see you next week.